Hi there. Today we're going to be going through a mini lecture kind of covering how you can get from alcohol to a carbonyl such as ketone and aldehyde and the reverse. Alright, so let's get into it right here. We're going to start with a primary alcohol. So just to reiterate what that's going to look like, a primary alcohol. There we go. This means here, we'll change colors, that there are going to be 2 beta hydrogens on here versus a secondary alcohol, which is going to have only 1 beta hydrogen on it. Change colors to that. And then a tertiary, which I'm not going to draw out, but that is just not going to have beta hydrogens on it, so it actually can't undergo these oxidation reactions. But that is something we can address later, so let's go into this one. A primary alcohol is going to be our starting reagent right here. Let me use this to show you. There we go. That's our primary alcohol starting material. And our goal here is to convert it to an aldehyde. So in order to do that, we need a weak oxidizing agent. Because, like I said, we have 2 beta hydrogens here. We need a weak oxidizing agent to allow us to oxidize only one of these beta hydrogens. If we use a strong oxidizing agent, what's going to end up happening is we end up converting it to a carboxylic acid, which is further than we want to go here. So we're going to look at weak oxidizing agents. I have PCC listed here as well as pyridine. PCC isn't the only one we can look at. I actually have a master list at the end of this, but it's just the example we're going to use for this mechanism. Okay, so what's going to happen here is we actually are going to the mechanism now. So our oxygen is going to have its lone pairs, and it's going to come and form a bond with a chromium from PCC. And as a result, to essentially make space, one of those double bonds is going to break, creating an ion right here. A little bit difficult to draw, but there we go. And you can see that over here as well, so that's what formed. Now we turn our attention to the compound down here. So the alcohol group is still intact, but we're now going to break that in a proton transfer. So an alcohol is now going to form on one of the oxygens of that chromium reagent, and so that's going to be pulled off, and we're still now going to have these lone pairs right around that oxygen for further reaction later. So now we have this group right here, that oxygen, and we're going to reform one of these chromium oxygen double bonds. At the same time, we're going to push off the chloride, which we're going to need later. Okay, so we come down here, and that chloride is still sitting around right here. It's going to be used to remove one of the beta hydrogens, the one that we're oxidizing here, and it is going to remove one of those hydrogens, and at the same time, this is going to break this bond right here and form a double bond. So this is going to end up forming is right here, and now we're breaking off what was the Jones reagent right here. So this is kind of an E2 mechanism. I'm not going to go into E2 as a whole, but that's what we're doing here, and at the end we end up forming an aldehyde as well as a well, what was our Jones reagent, but it's now kind of has our alcohol groups as well as that Cr and O double bond. And then we're also going to have that pyridine with chlorine, so that was kind of used to grab onto that hydrogen. So we now turn our attention to secondary alcohol. So I drew that in the last slide, so I'm not going to go back and redo that, but this is what it looks like, is this right here. There's going to be that 1 beta hydrogen just coming off right there. So because there's only 1 beta hydrogen, we can use a weak or a strong oxidizing agent, because after 1 round of oxidation, there's nothing to be further oxidized. So a strong oxidizing agent is going to do exactly what it needs, and same with a weak one here. So the example I have here is a Jones reagent, so that's going to be CrO3, H2SO4, and acetone as a solvent. First step here is kind of to prime it, so we have to break one of those chromium and oxygen bonds, going from double to single bond, And then we use that to form an alcohol using one of our protons from that H2SO4. So we come over here and we have, again, I'm going to keep calling it like a primed Jones reagent. That's how I see it. And by doing this, we are able to have the oxygen of the alcohol kind of almost like a nucleophilic attack coming right here and form a bond with that chromium. So it's a little bit small, a little bit difficult to see, but this is our alcohol group right here, right there. So it's kind of going to do this funny looking ring sort of arrow pushing reaction, which this is going to lead to the formation of some more alcohol groups, as well as pulling off the proton that was on the original alcohol. So you can see right here that alcohol is going to leave this right here, and that chromium is going to get protonated once again. The chromium reagent, sorry. So the oxygen on the chromium reagent is going to get protonated here. So from here we kind of have this messy looking compound, and now the goal is just sort of separate what we need because we have everything on here. So we have that one hydrogen right here that's going to be broken off, and it's going to give its electrons to that central carbon, and from there we will bring that down to reform a carbon and oxygen double bond, so a carbonyl, or in this case a ketone. And then deprotonation will occur. So at the end of the day, we have a ketone as well as a kind of protonated version of our Jones reagent. So since we just talked about aldehyde and ketone formation, from the alcohols, let's now talk about alcohol synthesis. So a good way to synthesize alcohols is using a carbonyl and some sort of nucleophile. A good nucleophile oftentimes is going to be your Grignard reagent, so that MgBr that's attached to, a benzene ring or just an alkane or an alkene or whatever it may be. So let's get into this mechanism. Oh, and to be clear, again, these reagents that are boxed in green aren't exclusive. Like, you can use them for other things, and there are multiple other reagents that can be used. These are just examples for the sake of a single mechanism. So to make that Grignard reagent, just to reiterate what you've hopefully learned up at this point, you're going to take an alkyl bromide, a benzyl bromide in this case, and you're going to react that with magnesium as well as ether, just to form that Grignard reagent right here, which again is very, very useful in organic chemistry. So now we look at a molecule here, a carbonyl. This is going to be a formaldehyde. Let's see right here that I'm drawing in. There we go. So we're now going to use that. We're going to start by breaking that carbonyl bond just to a single bond, which again will kind of create an ion out of that oxygen, which allows for space for the Grignard reagent to nucleophilically attack. That's how I'm going to put it, the carbon of the former carbonyl. And so now we have this compound right next door to it. But the problem is that we don't have this is not balanced. We have an ion right here, so a protonation will need to occur, and here we're just going to use water, weak base of water, and that is just going to be pulled off and form our alcohol group. And at the same time, we had that lone MgBr of our Grignard reagent, and that's going to combine, because that's positively charged, it's going to combine with our OH group of the water just to reform something. Another example of this is using propanol, so just a 3-carbon chain with a alcohol at the end. This is 1 propanol. We're going to start by deprotonating that. So again, we're kind of working somewhat backwards here now. We're going to take that alcohol, we're going to deprotonate it, so again to form that oxygen that is negatively charged, and from there we are going to, so that's kind of like a primed reagent, again, as I like to call it. We're now going to look at an aldehyde. So aldehyde right here. Again, we're going to have a nucleophilic attack here, and to, again, make space, we're going to need to break that carbonyl bond. So from here we have this kind of looking like an ether right here. What I'm talking about if you can't see my cursor, but we're still now going to have that lone oxygen that's negatively charged, so we just need to protonate it in order to form the alcohol. So it's kind of a formation of both an alcohol and an ether here, but again, that can be necessary depending on the situation, or as an intermediate to something else. Okay, so now we're going to go over carbonyls, using carbonyls with selective reducing agents. So I say selective reducing agent, I mean carbonyl specific selective reducing agents, because we have reducing agents that will reduce alcohols, for example. We have some that will reduce both alcohols and carbonyls, like Raney nickel. We just want to reduce the carbonyl here, and that's what's important. So we actually have two options for that. We have sodium borohydride, or we have lithium aluminum hydride, so LAH as it's commonly abbreviated. So what we're going to have is a nucleophilic attack to start. So to be clear, I'm looking at this aldehyde right here. We're going to nucleophilic attack at that carbon center, again breaking off that carbonyl bond right there, and that's going to form this guy, and the sodium of that sodium borohydride is just going to be there to kind of stabilize the charge, which is good. But what's going to happen is protonation, so we do need to protonate the oxygen up here, and that's why we broke that carbonyl bond in the first place. So we're going to use water, which is obviously weak, and it's kind of going to exchange, as I like to think of it. So that sodium is just going to come be with that oxygen. They like each other. Sodium hydroxide, it makes sense. So again, protonation, and then that's just going to exchange so that we have a final compound of sodium hydroxide, BH3, and an alcohol. Basically the same thing is going to happen with lithium aluminum hydride. We're going to have that nucleophilic attack again, so it's going to be right here that we're seeing that central carbon. Sorry, it's very difficult to draw with this. And with that nucleophilic attack, I just have a carbon here. I'm sorry, that is not the nucleophilic attack occurring here is going to be from that hydrogen. So that's the difference here, is it's not, yes, there's no, sorry, I apologize, there's no difference here. It really is a nucleophilic attack from a positively charged hydrogen, because that's what both of those compounds are supplying. So that's going to occur. We see that right here. Oh my goodness, we'll try that again. So that hydrogen was what nucleophilically attacked it, and then we're going to need to reprotonate it again. So we're going to do that from here, and then we end up forming our final compound of an alcohol. Okay, lastly, in terms of the reactions I'm just going to go over today, we're going to look at a more specific one, so carbonyl plus an oxygen nucleophile to go to a hydrate. So a hydrate is just it's two alcohol groups bonded to the same carbon. So this is, again, like our nucleophilic attack reaction that we looked at a few slides ago, but it's now specific to oxygen. So our oxygen nucleophile of interest here is going to be OH minus hydroxide, and that is going to be coming typically from a base of some sort. So that is going to nucleophilically attack our carbonyl carbon, breaking that bond to end up with a negatively charged oxygen. And after that nucleophilic attack occurs, we need to stabilize everything, so we end up protonating it using a weak base such as water. This both allows for our base to be regenerated. So again, we can use water in this reaction, because if we do that, we can then regenerate it very nicely, as you see here. And then after that is protonated, we have our hydrate formation. So I just wanted to summarize reagents, because that typically is the most difficult thing for me, is just like knowing which reagents to use when. So weak oxidizing agents I mentioned in regards to forming aldehydes from primary alcohols, because you can only use weak oxidizing agents there. But weak oxidizing agents can also be used in ketone synthesis from alcohols, from secondary alcohols. But again, I'll get into that in a second. So here we have PCC, which is the one in our example. I accidentally did write chromium trioxide here, so ignore that. That actually should be a strong oxidizing agent. There are quite a few strong ones. We can also use DMSO, so the structure is drawn here, and I believe I did an example with that as well. We have Swern oxidation. That's another one. I didn't draw the reagent out for that one, but that is another option. You can also use DMP, and you can use pyridine as well. So these are just like kind of quick. I mean, obviously it doesn't show you a mechanism, but it kind of gives you an idea of, like, let's say you're taking a test and a question came up and PCC was the reagent. Hopefully this gives you an idea that it can weakly oxidize whatever you're given. So let's go to strong oxidizing agents. Like I said, you can't use these with primary alcohols unless you're trying to synthesize a carboxylic acid, because it will reduce both of the beta hydrogens on that primary alcohol. But you can use them readily with secondary alcohols to form ketones, but you can also use weak oxidizing agents. Again, it's just because secondary alcohols only have one beta hydrogen, and so for to be oxidized, and so it's not a matter of like trying to oxidize something too far, too little. There's only one way to do it here. So for this, you can use those strong oxidizing agents. So KMNO4, H2CrO4, H2CrO. Sorry, I think I wrote that twice. That should be Kr2Cr2O4, Na3Cr2O7, Na2Cr2O7. We have a lot of options here, basically, and it shows you a lot of them are chromium reagents. Also, we have this one up here that I, accidentally put up there. But these are strong oxidizing agents, so if you see these come up, you should hopefully know what they do. And then we also have our selective reducing agents that are selective for carbonyls, so sodium borohydride and lithium aluminum hydride. Hopefully this gives you a good idea of what to do in terms of synthesizing carbonyls and alcohols from each other.